Hello everyone, welcome to today's class. Today we will discuss oxidative addition. In the last class we have seen the 16 electron and 18 electron complexes and the way they react. Today we will discuss one of the most interesting topic of organometallic complexes, that is their oxidative addition. Now, how the oxidative addition occurs and what are the criteria and how the complexes are varying, that is what is the topic of today's discussion. Now, if you look at the oxidative addition and if you try to deal with their rate law, then you will see if it is associative, then we will have first order with respect to ARX. Oxidative addition is happening in ARX. If it is dissociative, then we will have zeroth order with respect to ARX. That is the first thing we will see. Now, if you look at based on the associative and dissociative mechanism, if you look at delta S double dagger, then we will see associative case will give you negative delta S and dissociative case will give you positive delta S double dagger. Most importantly also, your molar volume in case of associative, it will be decreasing, and in case of dissociative, it will be increasing, right. Well, before getting into the discussion of the rate law, delta S and the molar volume, let us try to discuss with some real example first. Now, let us take a generic example, and that is LNM. It is a organometallic complex that will form, and you want to have oxidative addition of this ligand metal complex into AB. This is once again it is a generic example. You will end up getting LNM A and B. If the oxidation state of this one was N plus, at the end of the reaction you will have N plus 2. So, change in oxidation state is plus 2, change in overall electron count from the starting material is again plus 2. So, total 2 electron count increasing. If this is a 16 electron complex, this one will be an 18 electron complex overall now. If the metal was having N plus oxidation state, it will then have N plus 2 oxidation state. Now, if that is true, what you would understand that this cannot be a D0 metal, because if it is a D0 metal, then N plus 2 oxidation state will not be attained. So, it has to have more than 2 electron, more than or equal to 2 d electrons. Now, before going into the real example, let us try to take a non-transition metal equivalent or non-transition metal example. We have seen magnesium 0 reacting with any Rx organic halide to give you R, Mg and X. This is magnesium 2 plus 0 oxidation state giving you +2. Overall, this is an oxidative addition, example of an oxidative addition complex, right. Now, let us try to get back to these A and B. We are trying to discuss the generic reaction of ligand metal complex reacting with AB complex or AB organic species to give you ligand metal AB complexes. Now, we need to discuss what are the different variation of A and B. So, classes of A and B. We can have a polar AB or a non-polar AB, and we can have something where we have multiple bond, where AB bond will be retained. Let me give you an example, it will be clear. So, polar compound could be X2, X equals halogen, or could be HX, could be RX, could be RCOX, etc. These are polar AB. Non-polar AB would be hydrogen, silyl hydride, various silyl hydride, tin hydride, and simple alkane, and so on. AB bond can be written in oxygen during oxidative addition, or if it is a carbonyl of, or if it is an olefin, or if it is an alkyne, etc. So, 3 different classes of AB is possible. AB could be polar, non-polar, or AB could be the one where after oxidative addition still A and B bond will be retained. In the polar and non-polar example, we have seen that the bond between A and B will be broken, but in these cases at least one bond will be written. Again, the polars are X2, HX, RX, RCOX, acid chloride, and so on. Hydrogen, SiH, SNH, RH, all these are non-polar, and you can see oxygen or carbonyl species, olefin or alkyne. If you are having oxidative addition, then A and B bond will be retained. Now, there are 3 common pathways by which oxidative addition can occur. 3 different pathways. Let me write them down. 3 common pathways we see for oxidative addition. What are these? One could be concerted, another could be SN2, of course, the final one could be a radical one, right. 3 different pathways exist. Let us take an example, or the first example we would like to discuss is the concerted one, concerted pathway. So, today's class mainly we will discuss this different mode of oxidative addition. The first one is the concerted one. Now, you can take once again a generic example, LNM reacting with hydrogen to give you first a LNM sigma complex with hydrogen. Finally, it will give rise to LNM HH. So, oxidative addition into hydrogen is happening. You see the bond between the 2 hydrogen atom is broken in the final complex. Intermediate will be a sigma complex. Now, would like to discuss one of the real example rather than defining or keeping the M as one of the non-variant. Let us discuss this complex, iridium complex, I think you are quite familiar with this complex, iridium ditriphenyl phosphine carbonyl halide. Now, if it is X equals chloro, I think you might will know this complex, and that is known as Vaskaj complex, right, Vaskaj complex. Now, this Vaskaj complex, if X equals chloro, can react with hydrogen. Okay. Overall, it can give you from a tetra coordinated complex to a hexa coordinated complex. Okay. So, what we see here is this iridium tetra coordinated complex reacts with hydrogen to give you the hydrogen hydrogen bond broken species, that is now it is a hydride. How can you prove that it is a hydride? If you take the 1H NMR of this complex, you will see two peaks, one as minus 18.4 ppm, another is at minus 77.3 ppm. Thereby, this is again showing that this is a hydridic in nature, these hydrogen are hydridic in nature. And if you have X equals chloro, that is again the Vaskaj complex, delta H for this reaction is found to be 10.8 kcal per mole, and delta S double dagger for this reaction will be minus 23. Again, this is confirming the fact that this 16 electron Vaskaj complex undergoing an associative mechanism to give you this 18 electron complex, final complex. Further, how can you prove that these Vaskaj complex or Vaskaj type of complex, where X is varying, X equals chloro is Vaskaj complex, is really the one which is giving you the oxidative addition in a way you are looking at in here. To figure that out, what you can do is you can vary the X. X could be your iodo, bromo, chloro, etc. So, the electronic properties of X will change, and thereby you will see the relative rate of this iridium complex with respect to the hydrogen, whether X equals iodo, what is the rate of the relative rate of the reaction, to bromo to chloro, what is the relative rate of the reactions. Now, in order to do that, you can design the experiment where X is varying observation wise, experimental observation wise. You can see when X equals iodo, bromo or chloro, of course, electronic properties or electronic properties, you can see that it is lower in this case, this is higher for chloride, and the relative rate or relative reaction rate is great with respect to iodo, and bromo is little bit slower and chloride is the slowest one. What it is telling you is the Vaskaj complex, that is the chloro complex, will react with hydrogen the slowest, and the X when it is iodo, it will be the fastest reaction. Right. Now, again we will get back to this concept of ln m reacting with AB, in this case it was hydrogen. If it is undergoing this interaction, the transition state you will find is something like this, from which you will get ln m A B formation. Now, if this intermediate or the transition state is not really a cationic or anionic in nature, ionic in nature, then you would expect that solvent polarity will have little effect on the rate of the reaction. For the concerted reaction, the type of reaction we have drawn over here is a concerted one. For concerted reaction, in this transition state will have little effect or little bearing on the solvent polarity. So, if you change the solvent from polar to non-polar, your reaction rate will not vary too much in case of a concerted mechanism. So, this is one way to determine whether a reaction is undergoing a concerted reaction or not. To probe that, once again you can change the solvent. If the reaction rate is not varying too much, that will indicate that the oxidative addition is undergoing a concerted mechanism. Of course, the mechanism you cannot prove, it can suggest only. You have to do other experiments to further prove any mechanism. Now, let us try to take an example where in the last case we have seen a 16 electron complex is your starting material. You see an association of hydrogen with the 16 electron complex. So, hydrogen is coming and getting associated with your Vazquez complex or the 16 electron complex, iridium complex. Now, what happens when you have an 18 electron complex? Can you have a concerted mechanism for an 18 electron complex, and what would be one of the example? Let us try to give one of the example. Oxidative addition, which you can write down as OA, of different silyl hydride, different alkane, etc., usually can undergo concerted mechanism. Well, let us take example of a manganese complex, cyclopentadiene tricarbonyl manganese complex. This is once again an 18 electron complex. We would like to react this with a silyl hydride, a chiral one. I will come in a moment. Let us say this is a chiral silyl hydride, enantiomer pure, Now, this 18 electron manganese complex we would like to react with this silyl hydride. Of course, if you want to directly do oxidative addition into the silyl hydride bond, then the complex you will get is 20 electron, which is unfavorable. The first step then, what we would like to do is, we would like to treat this with light. We can expect an elimination of CO to give us cyclopentadiene manganese dicarbonyl species. From a tris carbonyl species, we now have a dicarbonyl species. Okay. From an 18 electron complex, we now have a 16 electron complex, which can then undergo oxidative addition into this silyl hydride bond to eventually give us this silyl complex, where you will get the silyl metal bond formation with the hydride being there and CpCO2. So, we have manganese complex with cyclopentadiene, 2 carbonyl, 1 carbonyl went out during treatment with light, and now the manganese is inserted in between the silyl and hydride bond. Okay. So, we have manganese hydride complex with silyl bound with manganese. Most importantly, what you will see is there it is undergoing a retention of configuration. The final complex will retain the stereochemistry of the starting silyl hydride. So, concerted mechanism, in this case a manganese complex which is an 18 electron complex reacting with silyl hydride, a enantiopure silyl hydride, to give finally the 18 electron complex. It does not react via an associative pathway, rather it undergoes a dissociative mechanism, where the starting manganese complex loses one of the carbon monoxide during treatment of light to give you manganese dicarbonyl cyclopentadiene species, which then react with silyl hydride to give you silyl hydride oxidative intermediate with manganese, where we have the final complex once again manganese with cyclopentadiene, 2 carbonyl, 1 hydride and 1 silyl moiety. Most importantly, this oxidative addition complex retain the stereochemistry of the starting material. So, stereochemistry can be retained during the oxidative addition if it is undergoing a concerted mechanism. We will come to the other example, which are SN2 in nature or radical in nature. Then in those cases you will be able to see what happens with the stereochemistry of the AB, that is the organic species where we will undergo the oxidative addition. Now, as you see, there is one example we have shown how light can be used to remove carbon monoxide. So, the unsaturation or coordinative unsaturation is promoted by shining light on the metal complex. So, the unsaturation was not there into the organometallic species. Unsaturation is created by the mean of an external source, in this case light. Is it possible to create this coordinative unsaturation to the metal complex by other means? Answer is yes, it is possible. We can have various approaches or various chemical reaction for these cases. For example, if we want to remove various other groups, then we can have various other ways to generate coordinative unsaturation. Okay. For example, you have seen if you want to remove carbon monoxide, the method you are using is light. If you want to use or remove halide, you can of course use the famous silver cation. If you want to remove alkyl, you can use proton. If you want to remove hydride, you can use this one, right. So, there are 4 different ways, for example, of course, there are many more. Clearly, you can remove a particular group from an organometallic intermediate. These are the usual practices. For example, if you have, I think it is very clear, if you have LNMX, you can react with silver plus to get LNM plus and silver halide and so on. Okay. So, what we have seen so far is a concerted mechanism, and in this concerted mechanism we have seen one example each of 16 electron complex and 18 electron complex, how the AB, the organic species, is undergoing oxidative addition with 16 electron and 18 electron complex. Next, briefly I will discuss SN2 mechanism of oxidative addition. Of course, we will discuss both SN2 and radical mechanism. today in next 5 minutes or so, I will try to briefly discuss SN2 mechanism. We will come back to that topic again in the next class. SN2 mechanism, as you would know, the ligand metal complex can react with A and your B in a way we have seen traditional organic reaction of SN2 type to give you LNMA, which is now an N electron complex, let us say. It was also an N electron complex. Of course, you are having B minus generated from this species. N electron complex undergoing reaction with AB in an SN2 fashion, where LNMA bond is formed and B minus comes out. Finally, you can have overall LNM a B and A complex. So, AB is now incorporated with metal to give you N plus 2 electron complex. The first step, as you can see, N electron complex will form the N electron complex. Now, we have interaction with M and A, then eventually this B minus will coordinate with M to give you LNM BA complex, which is now N plus 2 electron complex. So, you can imagine that such examples will be easy with something like methyl iodide. If A and B is methyl and iodide respectively, or methyl iodide will have such oxidative addition where SN2 reaction mechanism will be followed. Of course, if you have tertiary butyl fluoride, this will not undergo the SN2 mechanism. Well, in the next class, we will discuss much more about this SN2 reaction, their reactivity pattern. We will give you the organometallic complex and the real complex and their example, and discuss the mechanism of SN2 complex. We will also discuss in the next class the concerted mechanism versus SN2 mechanism and radical mechanism. Once again, the oxidative addition can be of 3 different types: concerted, the one which we discussed today, SN2 which we were discussing right now, and we will continue in the next class. Again, in the next class, we will try to discuss the radical mechanism for oxidative addition reactions. Okay, see you in the next one. Till then, bye bye.